In this video, we're going to go over what the formula to calculate arc length is and why it makes sense. So to get started, pause the video and see if you remember what it is. Okay, here it is. So if you're able to remember this formula easily, you can probably skip on to the next video. But if you took a little longer to remember, or you're not entirely sure why this formula is the way it is, then be sure to stick around so we can explain it. So first, let's get clear on exactly what arc length is. When we say arc length, what we mean is the length of this arc or the length of the function itself, if you want to think of it that way. So it's literally this length right here. You can imagine, or at least this is what I do, you can imagine that this is a string that's basically curved in the shape of the function. And then the question is, how long would it be if you pulled it taut and then put it up to a ruler? Whatever that distance is, that is the arc length between 2 points A and B. So that's what we're trying to figure out. But the question is, how do we figure it out? One clever thing that we can do is something when we were trying to find the area under the curve, except with a slightly different geometry. Remember how we found the area under the curve with integrals? We basically broke things into partitions, right? So we broke things into different sections, and then each of those sections had a certain, a width that we called delta x. And then basically what we did is we used a rectangle to approximate the area of each of those partitions. And again, there are many ways you could do that. You could use left Riemann sum, right Riemann sum, etc. when we're doing integrals, but that was essentially what we did. Here we can do almost the same thing, but with a slight change. Instead of actually using the areas of rectangles in each partition to approximate the area under the curve, what we can do is instead figure out these lengths. So if you figure out the length from this point to that point, and then this point to that point, and this point to that point, and this point to that point, and you just add up those lengths, add up the blue length on this diagram, hopefully you can see why that will give you actually a pretty good approximation for the length, the actual exact length of the arc, even though it's a little off. Like right here, it's more curved than our approximation is. But again, that's kind of the idea. If you can come up with a geometric formula to find the lengths between the different points at the ends of the partitions, you can just add those up. So that's what we're trying to do here. Now let's think about how we can do that geometrically. So let's focus specifically on the third partition here, and let's kind of blow it up, zoom out, or zoom in, and see what we can figure out. What we want to do is we want to find some kind of formula that tells us what this distance is, and I'm calling it delta S3 for the third partition. Obviously, you could have delta S1, delta S2, delta SK, etc. if you want to be general. But we want to figure out what this is in terms of things that we already know. And the question is, how do we do that? One clever thing that I'll say we can do here is we can actually use the Pythagorean theorem. So delta, hopefully it makes sense that delta S3 will be equal to whatever delta x3 is. So this would be like delta x3. And generally we try to keep all the delta x's the same for simplicity. And this will be delta y3. So if we have these, so if we have a way that we can figure out, let's say, delta x and delta y, rise and the run basically, for each partition, then you can imagine this as a right triangle, and this length we can find by the Pythagorean theorem. So specifically, we can find this. We know that delta s is going to be equal to, or I'll say delta s3, is going to be equal to the square root of basically delta x3 squared, that whole thing, plus delta y3. Actually, let me expand this a little. That whole thing squared. Just by the Pythagorean theorem. We know that. So that's good. And you can also abstract this to, I'll just write delta s instead of 3 here. Instead of 3, I'm just going to write k. Basically, this logic works for any partition. So if we're in the second partition, it'd be the same exact logic, just, the second delta x, second delta y, and second delta s. So what you can do is you can say delta sk is equal to the square root of delta xk squared plus delta y. Let me zoom down a little bit. Delta yk squared. That logic works for any partition. And the trick here is that what we can do is we can basically say the arc length is equal to, well, approximately equal to, remember this is only an approximation, it's equal to the summation of all the partitions. So from k equals, or two for these lengths along all of the partitions, let's say. And then n, remember n, just like with integrals, or just like with Riemann sums, n represents the basically the number of partitions. So in this drawing, I only have 4, but you could have more. So we want to keep it general. And basically, we're going to add up delta sk. So very simple. If we can find delta s1, 2, 3, 4, we just add them up. But what is that? We kind of already established that it's this, that it's equal to the square root of delta xk squared, just by the Pythagorean theorem here. Hopefully you can see that logic. And then delta yk squared. So there we go. This gives us this should give us a rough approximation for the arc length of any curve. Now that we have a formula to approximate the arc length, the question is, what do we do with it? Because remember, we're not trying to find an approximation for the arc length. We're trying to find the actual exact arc length. The answer to that is basically that we do what we did with Riemann sums. If we let n increase to infinity, as we let n get bigger and bigger, this approximation is going to get closer and closer to the actual values. So that's what we'll try here. Right now, you can see that I'm going between a equals 1, b equals 4. So a equals -1, b equals 4. So that's what we're trying to find the arc length between of the function sine of x. Here's the formula that we just figured out, basically. It's starting at 0 and ending. It's basically just has an index shift. You don't have to worry about that. It's the same thing that we just did, actually. And here you can see that this is the approximate arc length given by the sum of the length of these red lines, basically, these red dotted lines. And you can see it's actually pretty close to the original one already, even with n equals 2. But basically, the idea is that as n grows, so I'll just let n equal 3 now. Now we have 3 partitions. It actually got a little worse. That can happen. But in general, as you keep increasing n, it's basically guaranteed to get better and better, especially as n goes to infinity. So that's better. That's with 4 partitions, 5 partitions, 6 partitions, 7 partitions, 8 partitions. And I'm just going to keep going. Keep going, keep going. Right now, I'm at 20 partitions. And you can see that these numbers are almost indistinguishable, even at 20. Again, we're going to take n to infinity to really get the answer. But even when you go to 20, it's like pretty good. Similar situation as when you're trying to find the area under the curve. And then here you can see each one of these specific lengths is a straight line. So each one of these red lines is a straight line, whereas the curve might have a little bit of curvature. But it's so close that the approximation just becomes better and better. And the more partitions we have, the more we're going to zoom in even further, and the less that error will exist. That's kind of the idea. As we let n go to infinity, and I'm only going to go to 100 here. Again, 100 is still puny compared to infinity, but here you can see they're basically the same number at this point. And that is kind of the idea of what we're doing with arc length. So that's what we're trying to do here. But the question is, how do we actually come up with a formula to make this idea of the limit usable? In other words, how do we actually represent what we just showed here with a simple formula, hopefully? In other words, what have we learned before that allows us to add up, so to speak, an infinite number of infinitely small things as we have more partitions and the width of each partition shrinks? Hopefully you recognize that the answer is an integral. So let's take a little detour here to remind ourselves of what the limit definition of the integral actually is. I've covered this in another video, so I won't fully explain it here, but if you believe this formula, then all we really need to do is get our equation into this format, and then we can replace this whole thing with an integral. So let's do that. And effectively, let's start thinking about what's the problem here. You don't really need to worry about this so much. This is really just the function that you're integrating. The reason that what we have here is not currently in that format, if you think about it, is really because of the delta x. We simply do not have a delta x being multiplied on the outside here, whereas we do, so that in the limit, we do need that so that in the limit it can become basically a differential dx multiplied on the outside. And that's how we represent the integral. So we need to algebraically force that to happen. And then after we do that, then we can literally just take the limit as n goes to infinity of that to mimic what we just showed about the partitions, about how when the partitions grow, the answer becomes more accurate in the limit. and then that we can just replace with an integral. So that's what we're trying to do here. So how can we do that? How can we don't have a delta x on the outside. How can we, because we can't just randomly add one, right? That would change the expression. That would change the geometry that we've already figured out is true. This geometry is true. We just want to force it into that format if we can. The question is, how do we do that? The answer, hopefully, after looking at it for a while, hopefully you realize it's this. So let me do this. What you can do here, you can do kind of an algebraic trick. The first thing I'll say, before even going further, is that if you want to do this, you should make the assumption at the very beginning that the delta x in every single partition is the same. So in other words, you don't really need a delta x k. You don't need a different one for each partition. Just make the assumption that they're all the same, because that's what we want to do anyway to make our lives easy. It doesn't have to be that way, just to be crystal clear. If you're trying to approximate the arc length using this formula, you can use different widths for different partitions. But if you want to generalize the formula, like we're trying to do now, and take the limit as n goes to infinity, practically speaking, you are going to need to make the assumption that they're the same width. Otherwise, it's going to be too complicated to work with, and we're not going to be able to force it into the form of an integral. So let's make that assumption again. And if we're allowed to make that assumption, we should do it every time anyway, just to make it easier on us. Why have multiple delta x's if we can only have one? So that's what we're going to try to do first. And then what I'm going to do is this. Hopefully this makes sense. Inside of the square root, I'm going to factor out delta x squared. So if I do that, hopefully it's clear that I get left with 1 plus, I'll say delta yk over delta x, the whole thing squared. And then times on the outside, delta x squared. Actually, I'll write it like this. Delta x squared. So hopefully that makes sense. I'm literally just factoring out delta x squared from both of these. And if you want to confirm it, just basically distribute the delta x squared back in and verify that you get the same thing you had before. So that's good. What do we do next? And then you might be looking ahead. You might already see where we're going with this, but we can kind of algebraically manipulate this into that form after you get that trick. So remember, the square root is technically an exponent, and there is it's a fractional exponent, x to the 1/2 power. And there is an exponent property that says that we can basically apply an exponent. If you have two things multiplied on the inside of an exponent, you can apply the exponent to each of them individually and then multiply them. So let's use that property. That's helpful to us right now. So we can rewrite this as 1 plus, I'll say delta yk over delta x squared, and then times square root of delta x squared. But what is the square root of delta x squared? Well, the square and the square root cancel out, so you really just get the delta x. So there you go. That's what we were really looking for. Remember, our whole goal here, in order to get this in the same format as the limit definition of the integral, we wanted to force a delta x onto the outside. Now we have that. So if you just pattern match between these, and actually, I should mention, now that we've done it, again, all we've done, we haven't changed this. We've just algebraically manipulated it. It's still the same thing geometrically, which means it's still true, but also it's now in the form of a limit definition of the integral, so we can actually use the integral to do a lot of the heavy lifting here. So now what we can finally do is we can just take the limit as n goes to infinity, as this goes to infinity. And basically what that's going to do is crank up our partitions, the number of partitions, and we just show that the approximation gets better and better and more exact to the actual length of the arc as that happens, just like with integrals, just like with the area under the curve. So there you go. We now have this. Hopefully, looking at this, this is clear that if you kind of just pattern match one for one, this thing kind of becomes that. This thing kind of becomes the thing you're integrating. And then the delta x kind of becomes the dx. Hopefully, as you look at that, you can tell that on the outside, this is going to end up being some kind of integral. This is going to be some integral from x equals a to x equals b, and then dx. And then the thing we're actually integrating is 1 plus something, this is a little bit weird, squared. So hopefully it makes sense that just using the limit definition of the integral, like kind of on the outside, we can turn this thing into an integral, basically, because that's what an integral means. The question, though, and this is what's weird, this is something we haven't really seen before, is this. What do we do with this? This is, with delta x, delta y k over delta x. It's not exactly clear what to do with that as the limit of n, as the limit, as n goes to infinity in the limit, I'll say. So that's the question. What do we do with this? So you might not recognize it in this form, but this is actually the limit definition of the derivative. How does that make sense, you ask? Here's how. Think about it. As n goes to infinity, what does that mean? That means that the number of partitions increases. But as the number of partitions increases, I guess my question is, what happens to the width, delta x, of each of those partitions? Hopefully it's clear logically that that has to go to 0. If we have the same area between A and B and the number of partitions grows to infinity, then the width of each of the individual areas of each partition, or the width of each partition, I should say, sorry, is going to have to shrink to 0 as that happens. So this limit is effectively saying the same thing as the limit of delta x goes to 0 of that. And this, I'm claiming, is the limit definition of the derivative. So you can see the limit as delta x goes to 0 part over delta x. The only thing that doesn't look the same is this. Delta y, it should be f of x plus delta x minus f of x. But I guess what I'm claiming is that is what delta y equals. So if you think back to the original definition, the original limit definition of the derivative, it's this. Again, I have another video on why it's this, but I won't go into that here fully. But basically the derivative, I'll just say briefly, what the derivative means is basically the slope of a line between 2 points as you force those 2 points together. That's what we're really trying to do here. So you can see I've kind of drawn this out. Like here's x, and then you have a width here, delta x. So this is the x coordinate x. This is x plus delta x, the tiny change in x. And I've graphed these 2 points. Hopefully it's clear that the width, the width here in terms of the x value, between the x values is delta x, which I've written. But hopefully it's also clear that this is delta y. Delta y is literally y2 minus y1 if you think back from algebra, like the difference in the y coordinates. That is f of x plus delta x minus the lower one, f of x. So that's what that means. This is fundamentally delta y, is my point. And when you look at it that way, hopefully it's clear that, yeah, this thing actually is the derivative at that point. So it's literally the derivative at that point. So there we go. Based on that logic, this actually is the derivative at that point. And that is how we get the formula. Now, this is actually pretty interesting, I think, because this is the first time where we've ever used the integral and the derivative at the same time in the same formula. But it turns out that that is the way to think about arc length. So hopefully this makes sense. If you have any questions, be sure to leave them in the comments. Also, if you want to use the Desmos animation we used earlier in the video, be sure to check out the link in the description. Otherwise, I will catch you next time. See ya.